version of the elements that we did. So this is chapter 10, the one sample hypothesis. We didn't get to finish the slides in our class because they were quite lengthy. Just going to cover a few concepts here. So with your one sample test, I'm sure you're now familiar with the process. You have to define hypothesis and hypothesis testing. We've been doing it for a while now, where we get a statement, we define hypothesis, and we carry out the test, the 5-step process. Then we've been talking at length about a one-tailed and a two-tailed test, and how we conducted a hypothesis for a population mean, and how we conducted a hypothesis for a population proportion. Then lastly, we talk about the type 1 and type 2 errors. So what is hypothesis testing? You're trying to test a statement about the value of a population. So in other case, you want to check if a particular assertion is correct or not. Then you carry out the hypothesis test. So there are examples of hypotheses about a population parameter that are made. For example, the mean monthly income for system analyst is 3,625. Then you have another hypothesis. That one is a proportion that 25% of all customers at Povin Chop House return for another meal. So all those statements have to be tested through hypothesis testing. You want to test if they are valid and if they hold. So it is a procedure which is based, we have sample evidence, and it is grounded on probability theory. So you want to check if the hypothesis is a reasonable statement and should not be rejected, or it is unreasonable and should be rejected. So those are the bases of your hypothesis testing. And this is the first step test that you know now. You state your null and alternative hypothesis, select a level significant, identify whether it is a T or is a test. Then you formulate a decision rule. Then after formulating your decision rule, you calculate your test statistic. Then you either do not reject or you reject your null hypothesis. Then the important things to note, you have your null and alternative hypothesis. Then H naught and H alternative, these ones are mutually exclusive. Mutually exclusive implying that they cannot occur at the same time. You either accept H naught and reject the alternative, or the other way around. And H naught is always assumed to be true. So when we make a statement, we assume H naught is correct. Then H1 is the evidence which can disprove your H naught. So a random sample is of size n. We use it to either reject or not reject H naught. So if we conclude we do not reject H naught, it doesn't necessarily mean that the null hypothesis is true. It may mean we don't have sufficient evidence to reject H naught, therefore rejecting the null hypothesis, therefore suggests the alternative may be true. So not rejecting doesn't actually mean it is true. It might be because we don't have enough evidence. Then we have an equality sign that is always part of H naught. It could be equal to straight, equal to or greater than, or equal to or less than. So these are your signs for your hypothesis testing, where you have not equal to, less than, greater than, which is always part of your H1. Then you do set up your claim. In actual practice, you set up a H naught. Then if the claim is that we are possible, we can set up the claim as H1. So H alternative is the pattern, as I've already said. So you want to look into keywords to identify whether you're talking about a one-tailed, two-tailed, or right-tailed or upper-tailed, as we looked at before. See things such as improved, better than, effective, or has changed, etc. Those determined whether it is a one-tailed test, two-tailed test, or right or left, that terminology. So you have to pay attention to keywords such as improved, better than, or different from, or has changed. So the right-tailed test, the direction of the test, if you're talking about words, is improved, is better than, these depend on the variable being tested. But normally, If we're talking about improved or more effective, this is translated as less than, i.e. faster relief. So if you have better or more effective, it is less than. On the other hand, if you're talking about a test score, the words better or more effective can be translated as greater than. So it is important to know the variables that are being observed in order for you to tell whether it is less than or greater than. So in cases of time, better could mean less than. In terms of test scores, better or improve could mean greater than. So it is important to pay attention to what is said and the variable being investigated. So this is your null hypothesis. So we have errors that we're going to talk about. So type 1 error, the likelihood that we reject a true H naught. Then the type 2 error is we don't reject a false H naught. Important things to note there. Then we have parts of a distribution. The shaded part is a critical region. So in this example, this is a 95% significance level. Then you have a critical value of 1,65. This 1,65, you look at it from your Z tables, it is a critical value. Then the shaded region is the region of rejection. So if you have a calculated value which lies in that region of rejection, it means you reject H naught. Very important part to know. So you have a two-tailed distribution, which is non-directional, where your critical region is either greater than upper tail or less than a negative number, the lower tail. That is a two-tailed test. If you're talking about a one-tailed test, it is the lower left side that is shaded. It is less than a negative number. If we're talking about an upper tailed, it is greater than a given number. So that's your one-tailed. And that's your two-tailed test. It's important to know how to picture it mentally with the one-tailed and the two-tailed test. So as well, with equal to, if you have H naught mu is equals to certain value, then you have your alternative mu not equal to certain value. That is telling you that is a two-tailed test. So you look at the upper tail and the lower tail, which is why you have magnitude of Z alpha divided by 2. So your alpha is well, you divide it by 2. If you're doing a two-tailed test, you get your alpha value, you divide it by 2 to get your Z value. Then the test statistic there is bar x minus mu divided by sample standard deviation and divided by square root of n. That is your test statistic for a two-tailed test. Then we have your one-tailed test where it can be equal to or greater than or equal to or less than. In this case, the alpha value, take it as it is. In case of a t-tailed test, it will be n minus 1. Those are degrees of freedom. Then the t alpha value. Even for your two-tailed test, you see, even if you're using your alpha, it has to be divided by 2. Then you have n minus 1, which are termed the degrees of freedom. So those degrees of freedom are important because we use them when you're looking up values in a test. And the test statistics is bar x minus mu over sigma over root of n compared to the z test, where it's bar x minus mu over sigma over root of n. So with the z test, your population standard deviation is known. But for your t-test, your population standard deviation is not known. Hence, we use the sample standard deviation. Then this is the formula for a proportion. If you're testing for the proportion. So if you're testing for a proportion, it is the same information, not equal to two-tailed. Z alpha, you divide by 2. If it's equal to a greater, it's the right tail, it's the left tail. If it's equal to or less than, it is the right tail. So your H1 tells you whether it is a right-tailed or left-tailed test. So in the first one, it is your proportion less than a given value. So that one is a left tail. And you can see there it's Z less than negative Z alpha. For a right-tailed test, it is your Z rather than Z alpha, which is a right-tailed test. Very important to know the difference between the two. So here have an example. Jamestown Steel Company, which manufactures and assembles desks and other office equipment. The weekly production is 325 desks and it follows a normal distribution of mean 20 and standard deviation 16. Recently, because of market expansion, new production methods have been employed. The Vice President of Manufacturing would like to investigate whether there has been a change. So the keyword there is whether there's been a change. So this lets you know that you're dealing with a two-tailed test and you have a 99% significance level. That is what you would do to get the Z value there. You state your null hypothesis, mu is equals to 200, mu not equal to 200. So he has changed there. Then your level of significance is 1% as stated in the problem. You select your statistic. In this particular case, since your standard deviation, population standard deviation is known, we use the Z distribution. They are the two tails. So if you look at 1% significant level, you get your answer is 2.58. So we either reject H naught if your statistic is less than negative 2.5, or it is greater than 2.58. Then you do the calculation, which is pi x minus mu, divided by sigma over root of n. The calculation yields an answer of 1.55, which is not in the region of us, which is not in the rejection region. So in that particular case, we do not reject H naught. We conclude that the population mean is not different from 200. So we report that the Vice President of Manufacturing, we can see that the sample evidence does not show that the production has changed from 200 per week. So very important to know the statement and how to interpret it diagrammatically there. Then supposing the previous problem, the manager wanted to know if there was an increase in other way. Can you conclude because of the improved production method that the mean number of desks assembled in the last 50 weeks was more than 200? So you want to test if the mean number of desks assembled was more than 50. So we recall sigma 16 in 200 alpha 0.1. So this time we want to check if it has increased. So your null hypothesis, we check if it's equal to or less than. That is your null hypothesis. Then the alternatives, that's where we show that if mu is greater than 200, because we are testing if mean has increased, then your keyword there is increase. So if your keyword is increase, your H alternative should have a greater sign, which means we are testing for a right-tailed test. So the level of significance there is 1%. The test statistics is Z again, since your sigma is known. Then we reject H naught if it is greater than, if you look at the Z tables, a 1% significant level, you get 2.33. But since your value is 1.55, which is not greater than 2.33, it means we accept H naught and we do not reject it. H naught is not rejected, which means in conclusion, we conclude that the average number of desks assembled in the last 50 weeks is not more than 200, because we were testing if the average number of desks assembled in the last 50 weeks were more than 200. Then we have different types of errors. We have the type 1 error, which I've already said there's a probability of rejecting a correct H naught. Then we have the type 2 error, the probability of accepting a null hypothesis, which is wrong. So alpha represents the type 1 error, rejecting a correct null hypothesis, and beta is the probability of accepting an incorrect hypothesis. So we can also do what is called a p-value test, where you can observe a p-value to determine if a given alternate hypothesis is true or correct. So there is the p-value test. So when you're conducting a p-value test, you compare the p-value to your level of significance. If your p-value is less than the level of significance, then H naught is rejected. If your p-value is greater than a significance level, then H naught is not rejected. So we have this last problem where we are testing if mean has increased. So in that particular case, our Z value was 1.55, then our Z alpha was 2.33. So we reject H naught if your p-value is greater than alpha. So when you look at the probability of 1.55, you discover that the p-value is 0.605. So that value of, if you go to your probability tables and convert that Z value converted to a probability is 0.606, and you can see that it is higher than the significance level, which is 1%. So we fail to reject H naught again based on the p-value test. Very important there. So these are things that we need to know about your p-value. Something that I can ask you on in an exam. So if your p-value is 10%, there is some evidence that H naught is not correct. If your p-value is 5%, we have strong evidence that H naught is not true. If your p-value is 1%, we have strong value that your H naught is not true. Then if your p-value is 0.01%, we have extremely strong evidence that your H naught is probably not true. Then when testing for a population standard deviation, the sample standard deviation is used. So sometimes we can use the t-test under this condition. Number one, if your standard deviation is not known, population standard deviation, and later we'll see if your sample size is less than 30, you also use the t-test. So you have t, which is bar x minus mu over sigma, which is your sample standard deviation, divided by root of n, and your degrees of freedom are n minus 1. These are your statistics there, bar x being the mean, sample mean, mu being the hypothesized population mean, and s being the sample standard deviation, and n being the number of observation. So the t statistic is that formula. So for an example there, McFarland Insurance Company claims department reports that the mean cost to process claims is $60, and the industry comparison showed this amount to be larger than most of the insurance company. So the company instituted cost-cutting measures to evaluate the effect. The cost-cutting measures, the company selected a random sample of 26. The sample information is given below. So this is the sample of 26. So you are testing at 1% significance level if the claim that it is now less than 60. So this will correspond to your alternative you'll see later when we go to your H naught. So we're testing if it is less than 60. So that should be a direction of your H alternative. So your H mu is greater or equal to 60. Then as I said, your H alternative is less than 60. So always your statement, this one, now less should tally with your H alternative. If it is increased, it should also tally with your H alternative. And in this case, it's tallying now less is less than 60. As you can see, keyword now less, it tallies with your H alternative, which shows you that you have to use a small value, small less than sign, which shows you it's a left-tailed test. So the level of significance is 1% as shown in the question. Then we use a t distribution since your sigma is not known, population standard deviation. Then if you look in the t tables, you look at 25 degrees of freedom since you have 26 objects. Then we're looking at 1%. You're looking at 1% significant level. So this is a one-tailed test. So your 1% significant level, your answer is 2.485. Is that box. So you look at it from the tables, 25, then you look for 1% under one-tailed test, then you scroll down, that gives you 2.85. So 1% under one-tailed corresponds to 0.02 under two-tailed test. That's another way of looking at it. Then if you were to compute this on your Excel spreadsheet, this is what you're going to get. But now remember, we use descriptive statistics. It's no longer this mini tables in all the Excel program. Now we use your descriptive statistics as we have been doing in our practicals. Then that computed value, once you punch your 60 minus 56.48 divided by 10.126, it gives you 1.81. So that is your t-test, which is greater than negative 2.48. So you can see this lies within the acceptance region. So it means we do not reject your H naught since it doesn't fall in the rejection criteria. Hence, we have not demonstrated that the cost-cutting measures reduce the mean cost to less than 60. the difference between the two could be a simple manner. So there isn't that much difference between the mean cost per claims, and this difference between the population mean and the simple mean could just be a sampling error. Then again, now we're testing for your population mean with a non-population standard deviation, which is almost the same. Now we have 10 randomly selected hours. Then we have a sample standard deviation of 6, and we have a 250. So now we're testing, is the new machine faster? So if the new machine is faster, we expect a greater amount of units per hour, right? So current rate of producing, so we're expecting a greater rate per hour. So your else alternative should be mu, should be greater than whatever it is given. There should be your alternative hypothesis there. So when you come here, this is what you have. H greater, mu greater than 250, as I've said. Then H naught is mu equal to or less than 250. Then you select a level of significance, which is 5%. Then we use the t distribution because population standard deviation is not known and the sample size is less than 30. These are important conditions that we normally test in theory. So make sure you remember these conditions, as they're very, very important, as I'll test you these in your theory. Then as well, state the decision rule, 10 minus 1, which is 9. These are degrees of freedom. And you look at your t distribution, you discover that the critical value is 1,833. Then as well, you compute your value, 256 minus 250, get your value is 3,162. Since our value is greater than 1,833, lies in the region of acceptance, so therefore we reject null hypothesis and conclude that indeed the mean number produced is more than 250. Now we move on to tests that involves your proportion. So your proportion is a fraction or percentage that indicates part of a population and having a particular trait of interest. So a simple proportion is denoted by a P and is found by taking the number X divided by the N, where X can be the number of successful outcomes and N is the total events. So the test statistic for that is Z is equals to P minus theta 1 minus theta over N, where theta is the population proportion and P is the sample proportion. So if your population proportion and your sample proportion, then you have N, which is the sample size. So a random sample is chosen from the population. So these are the distributions that we're going to use if you want to conduct a test for a population proportion. We assume that the sample data collected as a result of counts, and we assume that there's an equal likelihood of success or failure, which are equivalent to the binomial assumptions that you guys discussed in chapter 6. Also, the probability of success of each trial is the same, and the trials are independent. Then this test will be conducted, and you're going to use N and 1 minus theta. They are least appropriate. So when the above conditions are met, you can make your normal distribution, which can be an approximation to your binomial theory. So there you have P, sample proportion. Then you have your theta, hypothesized population proportion. Then you have 1 minus pi and all of that. So we have that question. Suppose prior elections in a certain state indicated that it is necessary for a candidate for governor to receive 80% of the vote in the northern section of the elections. The incumbent governor is interested in assessing his chances of returning to office and plans to conduct a survey of 2,000 registered voters in the northern section. So in the survey of 2,000, the potential voters revealed 1.5 plan to vote for the incumbent. So the proportion there should be 150 divided by 2,000, as you see. So we want to test what are we testing for? Because this is an election. So we are testing if the governor is going to receive at least 80% of the vote. So it means your null hypothesis should state equal to or greater than 80%. That is what your null hypothesis should be. and you'll see there your alternative hypothesis, you have equal to or greater than 80%, that's your null hypothesis. Then the alternative hypothesis is a proportion less than 80%. So at least is the keyword there. So at least means equal to or greater than. Then we select the level of significance, which is 1% as stated in the problem. Then we select the test statistic. Since we are using a Z distribution, since our assumptions, if you multiply n number of objects times simple proportion, or n multiplied by 1 minus n, it's all giving you a value equal to or greater than 5. So we use a Z distribution. So you calculate your value, you discover that it is 2,80, which is after establishing this, since we have established your alternative said your proportion should be less than 80%. So based on the alternative, we can conclude that your critical value is 1,85. That is your critical value. So when your critical value is 1,65, we reject H naught if it's less than 1,65. And when you compute your value, it is negative 2,80. And negative 2,80 is indeed less than negative 1,65. It lies within the rejection region. So therefore, we will have to reject H naught. We reject H naught and conclude that the difference between the 2.5% between the sample percentage and the hypothesized sample mean is statistically different. Therefore, it does not support the claim that the governor will return to the mention for another 4 years. So make sure you understand your conclusion and interpret it in the proper manner it should be done. So that is it for that marks the end of chapter 10. So these are the important elements that you need to know in as far as this chapter is concerned. All the best. See you in class and prepare for your assessment, which is coming, which should be semester test 2.